And hello, welcome to this video. So in this video, we just pick up where we left off. We know that these terms here are non-dimensionalized numbers, and we want to have this term so that it's easy to do differentiation of the pressure drop equation without needing to consider units so much. As long as we keep working with non-dimensional values, then we just substitute it back into our chain rule, then we can find our Jacobian like so. Right, so the thing is this, okay, so what's the non-dimensional number that's closest to this? Okay, is actually the Bejan number. Okay, Bejan number is defined as so. Okay, at least the units of those they are defined as so. Delta P L squared over mu A or mu alpha. This is the Bejan number. It's a non-dimensionalized pressure drop. Okay, the delta P here, even though it's lowercase, that represents a dynamic pressure drop rather than kinematic pressure drop. So okay, so this is if you have heat transfer, of course. Okay, for heat transfer, it is defined as, okay, I'll put it here, Bejan number equals to fraction of what? Delta P, okay, some length of the channel squared, and then after that divide by alpha and the kinematic viscosity, okay, or rather dynamic viscosity. Okay, so delta P L squared over mu alpha. Okay, I will try to keep it the same as Wikipedia so that at least it's easier to read. Okay, easier to reference. Okay, so this alpha is thermal diffusivity. Alpha is thermal diffusivity, which has the same units as momentum diffusivity. Okay, so this is new. So this is also known aka kinematic viscosity. Alright, so this is how it will work. Yeah, so this is how it will work. Yeah, and of course you can find all of this in GitHub. I will kind of put it there under MIT license, so it's free and open source. Yeah, can use it. Okay, so yes, what am I saying here? Yes, so this delta P L squared over mu alpha. Okay, this is what the number is. Okay, we can change the mu to nu times rho, right? Okay, we can of course rewrite it in terms of kinematic pressure. Alright, so I can actually change this to nu, and then I'll have a rho inside here. Okay, so once I do that, I just divide top and bottom by pressure, and that is it. Okay, so this is the Bejan number using kinematic pressure, noted by small p rather than big P. Right, so this is how the Bejan number will look. Well, I can just as easily swap this thermal diffusivity for momentum diffusivity here. So that's what I actually wrote earlier. So let me just put it here, so that at least it makes more sense when you read it. So I can change the alpha to a nu at the bottom, and that's how we get our Bejan number for this case. Alright, so this is in the fluid mechanics version. You see in Wikipedia. This will be under the paper formation of wall jet near high temperature wall under microgravity, blah blah blah. At least that is the fluid mechanics version. Okay, but suffice to say, regardless, this thing is definitely non-dimensional. So we'll just define the Bejan number as so for this case. We define Bejan number as follows for pipe. Okay, so we'll use this, and then we'll just say L is pipe length. Okay, L is pipe length. Yeah. Okay, of course, the other way to do Bejan number is using this using D instead of L. Okay, using D instead of L for that. Okay, but I'll rather stick with the L so that it's kind of consistent with the way we write. We are not going to base it on diameter, but rather on the channel length. Okay, so L here, L is the fluid path length rather than the diameter. So I'm just going to have this L squared term on top here. Now you see this term here almost looks like Bejan number, except we have D squared instead of L squared. So I need to move the L squared elsewhere. Okay, so how are we going to do it? So this is how I actually non-dimensionalize the equation to kind of include the Bejan number, right? So I want to change this. I want to have an L squared in the numerator, right? So I want to have an L squared here in the numerator. Okay, I want an L squared here in the numerator. So what do? Okay, I'm going to multiply L squared to the top and bottom in the denominator. So I have an L squared over D squared and a nu squared over L squared term in the denominator. And then what do? I bring this nu squared over L squared on top. Okay, so this nu squared over L squared I bring on top, so the top almost starts looking a little bit more like the Bejan number already. Okay, so if you take a look here, the Bejan number is delta P, as in kinematic pressure, L squared over nu squared. So this thing up here is already the Bejan number. Okay, so again, I just multiply the top and bottom by L squared, so I get a nu squared over L squared term. Okay, nu squared over L squared term, then I bring it to the top, and then I just get the Bejan number like that. And I'm left with 4L by D, half L squared by D squared at the bottom here. Okay, all of these terms at the bottom. So what do I want to do? I want to use the 4L over D 4L over D dimensionless number, so I want to keep to that. So since I have a L cubed term, L cubed by D cubed term, I want to have a 4L cubed over 4L over D, and then the whole thing I cube it. So that's why I'm doing this. I'm making the 4L over D cubed term, and I'm bringing 16, changing half into 16 over 32, so that I can bring the 16 in here, so that because 16 is actually 4 squared, I can bring it in here, and then I'll have 4L over D, whole thing cubed. So I have a 1 over 32 term here, and I will bring it to the numerator, and that's where we sort of have our thing. Okay, now the thing is fully dimensional, non-dimensional. Okay, so now we have a fully non-dimensionalized equation. Alright, so remember, the whole reason why we do this is so that it's easier to plug it into our program. Okay, so that we don't have to deal with so many terms. I just need to have 2 inputs in order to find the Reynolds number. I just need a Bejan number, and I need a length to diameter ratio, and that's enough. two inputs there, and that will actually solve for the Reynolds number. Okay. Now, of course, it should be noted that this F over Reynolds number, or rather this fanning friction factor, as you can see from the Moody chart, okay, this thing is not exactly that nice, in the sense that one fanning friction factor can have multiple values of Reynolds number. Take, for example, fanning friction factor of 0.04. Okay, a fanning friction factor of 0.04 can have a Reynolds number in the laminar region. It can also have a Reynolds number in the turbulent or transition region. Okay, that's a little bit, actually that's pretty troubling, because you cannot just expect to supply one fanning friction factor and then you expect to get one Reynolds number. So that it doesn't work that way. However, when you actually multiply this Reynolds number square back, you should be able to get 1:1 ratio of a fanning friction factor to times Reynolds number square to some pressure drop value or some Bejan number value. Okay, why? Because when you multiply the Reynolds number square into this whole thing here, when you multiply the Reynolds number square into this whole thing here, you can see that this whole term here is actually 16 or 64 over Re, depending on which friction factor you use. So the initial like non-dimensionalized pressure drop will be sort of linear with Reynolds number, and after that you start having sort of a non-linear relation. So you keep having a Reynolds number go up, but this thing over here indicates that it starts being more and more non-linear. So as you have the slope down 64 over Re, this actually represents linear flow, where you have like what do you call that? Ohm's law is obeyed. This is a very linear relationship between the pressure drop, okay, between pressure drop and Reynolds number, or in this case mass flow rate. Okay, so Bejan number and Reynolds number, they are linear within this laminar flow region, and within the fully turbulent region, they are more or less quadratic relationship. There's a square term here, so mass flow rate equals to square root of delta P, or else the other way around, delta P equals to mass flow rate squared. So you can sort of have that squared relationship preserved as Bejan number goes into Reynolds number. Okay, so in the middle is just somewhere in between, but all the while the Reynolds, the pressure drop is actually increasing. So physically speaking, the pressure drop in the laminar flow region will not be the same as the pressure drop in the turbulent region for the same pipe. Okay, if you have one pipe, you will definitely have a lower pressure drop in the laminar region as compared to the transition region, as compared to the what do you call that? Fully turbulent region, or even the turbulent region. Yeah. So this is something that helps when we actually shift the Reynolds number squared to the left hand side. So it's a 1:1 relationship. If it's a 1:1 relationship, we can definitely use those root finder algorithms to ensure that we just have one value of the Bejan number to return. Okay. So we have our equation being fully non-dimensional. So we can use this term. Okay, we can actually differentiate Bejan number with respect to Reynolds number. Okay, differentiate the Bejan number with respect to Reynolds number, and then we can find our desired differential, d delta p dRe. Okay, d delta p dRe. So remember, d delta p dRe is what we want to find out. We can actually find that out. Okay, but in terms of calculation, it's a little bit easier to do the Bejan number d delta p times d delta p dRe. So we actually change our whole equation to this, so that we do not need to worry about one friction factor actually having two what do you call that? Yeah, two values. Okay, so this is also another good reason to non-dimensionalize the equation, so that we can have 1:1 relationship between pressure drop and pressure drop and what do you call that? Pressure drop and Reynolds number, or non-dimensionalized pressure drop and Reynolds number. Okay, so let me write this down. So it is also very important to computation, to our computation algorithms, that one pressure drop corresponds to one pressure drop value corresponds to one Reynolds number value. So we don't have the problem of one friction factor value corresponding to two, what do you call that, two Reynolds number values. Okay, so that's an important thing to note. Okay, so we can actually from this equation find out the Bejan number, the RE, that's a total differential. Then we just use chain rule again to separate out two. Then we'll have the delta P, the RE, which is what we want to find, and the Bejan number, the delta P. So we'll have a function to so-called find this, the BE, the RE, and then we will have several other functions to do those substitutions and everything else to take care of things one at a time. And then of course in the final code we'll just strip out most of the derivation and then make it more succinct so that it's easier for you to read. Here is actually the full blown out thought process, which is why I put it in the fluidPipeTheory markdown file rather than I put it inside the code readme file. Okay, so this is a much longer version. So we can start finding this term on the left hand side by differentiating the friction factor using Churchill's relations, and then I multiply it by the Reynolds number square. So what I have done here basically is to have the Reynolds number to calculate this value, FRE times RE squared. I actually want to multiply the Reynolds number inside this equation so that it's easier to differentiate. At least in my opinion, easier to differentiate. Because I don't want to keep doing product rule. I rather multiply the Reynolds number in, and I don't have to do a 1 over Reynolds number differentiation. So you can see for this first term on the left hand side, okay, I have RE squared here times the fanning friction factor. So I change it into a 1 over 12 power. So this is actually RE to the power 24 times 1 over 12. So I multiply RE over Reynolds number to 24 in, and then I bring it to the left hand side. Okay, so Reynolds number square over Reynolds number, that is just 8 RE. Okay, this one's superbly easy to differentiate, so no problem. So I have RE over 24 here, so I'll start dealing with this side now. I bring the RE over 24 in here. So RE over 24 is actually Reynolds number to the 16 times 3 over 2, so that I have the same powers on both. Then I can bring RE to the 16 over here. Okay, so now I have this. I have these two things to differentiate. With this, I can sort of start doing some kind of a substitution or chain rule differentiation over here, rather than doing product rule, so that I just need to find the inner derivative of this, and that should be fine. So I'll just define this big term here, this term in the inner brackets as G1. Okay, so I'll substitute the term here. So d by dRe of this thing here is d by dRe of 2 times G1 to the power of 1 over 12. Okay, so this big thing inside here is G1. So I want to start segregating my different derivatives. So G1 here is 8 RE to the 12 over RE 16 over A plus B. Okay, so this RE to the 12 here is okay. So so this is the G1 I will deal with later. I will start differentiating this side first. Okay, So how do I differentiate? Okay, so I will have I'll bring the power down, okay, 1 over 12 down, so I have g1 to the power 1 over 12. Then I will reduce the power by 1, so that means I will multiply by 1 over g1. Okay, so I'll have a function to compute 1 over to compute g1 and 1 over g1 for sure, so that yeah, I'll have the proper things later. I'll have the g1 later on. So g1 is a function of re, so this g1 here is this big thing. Yeah, so I just multiply the 1 over 12 to the 2 in front. I'll have 1 over 6, and I'll just leave this thing as here. So I will have two functions to help me out here. One is to return the value of g1, and number two, I want to have a function returning the value of dg1 dre. So I start planning out my program over here. Okay, now I have a dg1 dre. So I will have a function calculating g1, of course, that's fine. Now I also want to have a function calculating dg1 dre. Okay, so next challenge is to differentiate dg1 dre. How do I differentiate dg1 dre? Okay, dg1 dre can be done as the following. So d by dre of g1 equals d by dre of everything on the inside here. And let me just check whether my Churchill friction factor is correct. Okay, so yeah, 8 over re to the power 12. Okay, of course I multiply the Reynolds number inside. So, and then over here is 1 over a plus b to the 1.5. So this is a 3 over 2 power. I have a Reynolds number to the 16. Okay, shouldn't be too bad, right? I did it step by step. Of course, if you find errors, just let me know. Okay, of course, differentiating this, the first part is easy. 8 times re to the 12, you differentiate it. Okay, bring the power down. Okay, multiply the front out here. Then you reduce the power by 1, you get Reynolds number to the 11th power. Okay, so you get Reynolds number to the 11th power. This is the laminar term. Okay, the laminar term. Okay, so the laminar term is out here. Actually, yeah, I should actually multiply the 8 times 12 out. It makes it a bit neater. So what's 8 times 12? I think it's 96. Yeah, 96. Mental sum's not too bad. Okay, where's the yeah, I'll put it at the I'll put it over here. Yank this, I'll paste it here. I'll change this to 96. Okay, 96 times Reynolds number to the 11. Now let's deal with this monstrosity over here. It's not that much of a monstrosity. I actually just need to do the usual chain rule on this thing. So what do? Again, bring down the power here, reduce power by 1, so instead of 3 over 2 I get 1 over 2. Then I need to differentiate the inside. So d by dre of re to the 16 over a plus b. Now we have reduced everything down even more. Okay, then once we have this, unfortunately we start needing to use a little bit more complicated quotient rule. Okay, the quotient rule. So how do we start the quotient rule? I think I already made a few careless mistakes. I spotted a few careless mistakes here. Okay, but the quotient rule is as follows. Okay. Oh wait, I have not done that careless mistake yet. Okay, so quotient rule is as follows. So just pay attention to this term over here, the one I'm highlighting. So bottom constant, a plus b, we differentiate the top part, Reynolds number to the 16. So differentiate the top part is here, the bottom constant is here. Alright, so that's fine, that's over there. And then top constant, RE16, a top constant differentiate. Oh shucks, yeah, see, careless mistake. Yes, I have careless mistakes. So let's make, I'll need to do some correction here. Need to put a minus sign. So bottom constant differentiate top. Okay, bottom constant, differentiate top. Okay, a plus b, differentiate top is 16 RE to the 15, so that's already differentiated. Minus top constant, differentiate bottom, so this Reynolds number thing here, it should have a minus sign. Okay, it's a minus sign here. Oops, wrong one. Wrong one again. Yeah, that's when equations get really long, unfortunately. Yes, now the thing is in the right place. It's a very long fraction, so I think I want to, let's see, I want to shift this 3/2 thing to the next line. Yeah, so at least you can see. Okay, so minus RE to the 16. Okay, so that's all that is remaining. Yeah, so I have a d by dRe of a plus b times RE to the 16 over a plus b times RE to the 15. Okay, then of course I have the 96 RE to the 11 over here. Okay, 96 times RE to the 11. Yeah, 96 times RE to the 11. Then you have all these terms on the right hand side here, which represent the derivatives. Okay, so this is the entire derivative here. Okay, so Reynolds number to the 11th is quite okay to calculate. You can use a function to do that. Reynolds number to the 16 over a plus b, again also quite easy to calculate, provided you have a function for a and b. Okay, and then this term on the right hand side here, most of it is quite easy to calculate. Reynolds number to the 16, you can use a function. A plus b, again easy to calculate if you have a function to do that for you. Reynolds number to 15, okay, again easy if you have a function for you. A plus b to the square, a plus b squared, let the function do the addition and multiplication for you. I'm not going to expand it out. The only thing that I need to concern myself with analytically is this value, d by dRe a plus b. So d by dRe a plus b is actually d by dRe of a, d by dRe of b. Okay, so I need to differentiate these two terms separately. Again, there, as you can see here, there is some error for my a and b. Okay, why did I just happen to? Yeah. So let me change the a to make it right. Okay, the a should be to the power of 16. Alright, and this should be to the power of 16. Alright, and the b is, okay, b is harder to get wrong, so let's close this. I'm not going to save. Okay, Churchill equation, 2.457 times ln 1 over 7 over RE to the 0.9. Okay, so I have 7 over RE to the 0.9. Okay, 7 over RE to the 0.9. I need to change this accordingly. So first thing first, yeah, we'll need to make a few changes. I'm going to use the power law to bring out this fraction term to the front, so that I have minus 2.457 in front. Okay, again here 7 should be on top, Reynolds number should be at the bottom, so let me make that switch. 7 on top, change in word, RE at the bottom. So this is the correct equation, both of them to power 0.9. 0.27 times roughest ratio. I need to put this to the power of 16. Okay, I kind of forgot to do that. Put this to the power of 16. Okay, and now let me use nicer what do you call it, brackets. Okay, so I use the left and right square brackets, and this is what A should be like. Okay, so A is this, and want to differentiate this, well, I'm going to again use another term called G2, and that will help me differentiate whatever is on the inside. Okay, so G2 is again, I need to change the word, 7 over Reynolds number. Okay, 7 over Reynolds number times plus 0.27 times the roughness ratio. Okay, so how do I differentiate dA dRe? Okay, dA dRe, well, yeah, I have to change this part as well because I did not include the power 16 thingy here, so I need to change this. Let me change this here. So dA dRe, so this is A, right? So I'll have this whole thing over here, and I'll need to slowly differentiate right in front of you. It's not ideal, but I'll yank this and 6 down. I'll paste it here. Okay, so I need to d by dRe of this everything. So yank this, paste it in front of the equal sign, take out the A. Oops, take out the A. So d by dRe of everything here. Okay, for simplicity's sake, I will start replacing it by G2. So let me go 8 up, yank this, paste it here. Yeah, I'll change the inside to G2. Whatever's inside this logarithm, CI bracket. Oh no, that doesn't work. Okay, so the bracket thing I will leave it out. I'll just say that this bracket term here is G2. So ln of G2, alright? And let me use the right, yeah, so that I'll have a proper logarithm notation here. Yeah, I think I want to put the logarithm notation properly as well. On top, 3 up, yeah. Let's do it carefully, so I have all the ln's being properly logarithm. Natural logarithm, okay, log natural ln. So I have a G2 here, and this whole term inside here is A. So let me also put A 14 up. Okay, my ln. Okay, change this. I want to change this to G2. Okay, so this makes A a lot nicer to write. Okay, so how do we differentiate this? Okay, so we'll start the messy work now. Five open, yank this and paste it here. So first thing first, let's bring the power down again. Fraction. Okay, I don't need a fraction here. Just bring the power down. This is 16. In front, let me remove the differentials. Oh wait, I won't remove the differentials just yet. So bring the power down, reduce the power by 1. So I need to put in here. Yeah. Put in here. I'll put fraction A divided by So I'll reduce the power by 1, meaning to say I need to divide by the inside of this term here. So minus, okay, let me put inside a fraction here, minus 2.4457 ln of G2. Okay, 2.457 times ln of G2. So this is how we get the, I have this whole thing inside here to the power of 15. So it's basically A over minus 2.457 ln G2. Then I will, of course, differentiate the inside. So I will take that 16 out to the power of 16. Okay, and that's what I need to do. Okay, I'm going to move on to the next line. And what am I going to do? I'm actually going to bring this 2.457 out to the front. So I'll bring the 2.457 out to the front because that's just a constant of multiplication. Okay. So I'm going to put this out here. Minus 2.457. Yeah. So you can see this part is very nice for us because this will just cancel everything out. Okay. Okay, so we are almost there, almost there. So the 2.457s will cancel out. So di bracket xx, and I'll cancel this out. So this will be what happens. And what is this? Okay, this is a easier. It's getting easier. Okay, or rather, we are almost there, almost there. Okay, so it is 1 over G2 times d by dRe of G2. Okay, so let's have a 1 over G2. So let me put a G2 ln G2 in front. G2 times ln G2 in front, and d by dRe of ln G2. Oh yeah, I mean we already have the expression here. So this should be the right expression for dA dRe. So 16a, maybe I'll put the 16 in front. 16a G2 ln G2 d by dRe of ln G2. So let me just put the ln G2 here, ln of G2. So for this function, it's just dependent on two things here. One is alright, I should take the ln out of here. Okay, so it's just dg2 dRe because the ln of G2 is 1 over G2 times the differential of dg2 dRe. So there are two things over here. So we need G2 and dg2 dRe. Okay, so we need those functions to return the approximate values. So I'm going to have a function to calculate G2. I'm also going to have a function to calculate dg2 dRe. Okay, so what is dg2 dRe? So G2 is 7 on, as you can see, 7 on top, Re at the bottom. So I'll need to do some changes here. 7 on top, Re at the bottom. CIW7, CIWRE. Okay, 7 on top, Re at the bottom. So how do I differentiate this? I have to change some things, of course. Okay, first thing first, Yeah, I have to get rid of this. All this doesn't make sense. It's confusing me. Okay. So d by d re of g2 is actually d by d re of 7 times 7 to the power 0.9 over re to the 0.9 plus, of course, there's a constant here. The constant will just disappear. Okay, maybe I'll just put that in front so that there's less ambiguity. The constant is supposed to disappear. Okay, plus 0.27 times fraction var epsilon over d, and that's what happens. So let's do this first. Okay, the fraction constant with roughness ratio disappears. Okay, so let's just do that extra step so that it's less confusing for a first time reader. Okay, and all we are left with is d by d re of 7 to the power of 7 to the power of 0.9 over re to the power of 0.9. So 7 to the 0.9. Now this thing we can just bring it in front, right? Can just bring it in front. Now paste it here. Now I just have 1 by re to the 0.9. Okay, then this one to differentiate it, okay, straightforward. Okay, I need to bring the power down. Okay, the power is actually minus 0.9. Or maybe I'll just put Reynolds number to the minus 0.9 over here so that it's easier to see. re to the power of minus 0.9. Okay, bring the 0.9 r down. Okay, reduce the power by 1. So, and then differentiate the inside. Okay, so the re is just 1. So I will just have at the end of the day minus 1.9. Okay, so I'm just going to pre-calculate this number minus 0.9 times 7 to the power 0.9. If not, it's very slow for the algorithm. So 7 to the 0.9 because 7 to the power 0.9 times minus 0.9. Okay, minus 1.58. Okay, I'm going to paste it as a number. Okay, I'll just keep copying till the first 0 pops up. Okay, I'll just paste it here. 6 up, open the line, open paste. So yank and paste. So this at least makes the front part less intimidating. No need to calculate anything. So d by dg2 is just this number in front times re to the minus 1.9. Okay, so again 7 to the power 0.9 times minus 0.9. Okay, then you multiply by re to the minus 1.9. Okay, so d by dg2 is pretty straightforward. Okay, once we calculate it. Okay, paste. Alright, so dg2 dre is this thing here. It reduces to something very simple. but it's taken a fair bit of work to do all this analytical differentiation. Now, why are we doing it analytically? So that we can be confident that there's no error with regards to numerical differentiation. That's one reason of doing it. Second, maybe it's faster computationally, because instead of evaluating the function so many times, then doing the division, maybe it's easier to just go through these steps of evaluating all these numbers. Okay, so we have d by dg2 of re, which we can then substitute back in here, and then so on and so forth, all the way backwards till we find our derivative. Okay, so second reason why we want this is because we want to make sure that if we differentiate our equation analytically and using numerical methods, we want to make sure that there is a match, so that at least we have some confidence that is internally consistent. Okay. Of course, the benchmark will be the numerical ones, I guess, because one can always make careless mistakes here. Okay, one can always make careless mistakes here. But at the end of the day, this is very important to do because of the Jacobian. We want to work it out by hand. So that it might be faster to calculate. Okay, but we'll have to have a series of tests just to make sure all of this is okay. Right. So last thing over here is to consider the derivative b. So we'll need to differentiate this as well. So that's very simple. We just bring this constant out to the power of 16 times re to the minus 16. And to find the derivative, we bring the power down, reduce power by 1. Okay, differentiate the inside. dre is just 1. So Reynolds number to the minus 16 is here. Okay, 37530 to the power 16 here. So both of these can be combined back into the b. Okay, and once we have b, we can just multiply that b by minus 16 over re. So db dre is just this thing right here. Okay, db dre is minus b times 16 over re. Okay, so that's more or less it. Okay, we have all the derivatives we need, db dre and da dre. Okay, so dA dre is actually g2 ln g2 or dg2 dre, which is this number right here. Okay, so we can substitute back those things. Okay, substitute those back into d by dre of a plus b. Okay, d by dre of a plus b can substitute in back here. Reynolds number can substitute in back here. A and b, once we calculate it, we have those equations already, a and b. We can just develop functions for them, and we can just substitute those back in here as well. Okay, I'd rather use this expression of a. It may be faster for the computer, because the computer doesn't like to do, it's slower to do fractions. So try to avoid fractions as much as possible. Okay, so these things here are good. They look good. You have re to 16 over a plus b. You have a dg1 dre. dg1 dre can be used to substitute right here, this big thing here. You can calculate g1 using this formula and just raise it to the appropriate power. So 1 over 6 times dg1 dre times g1, 1 over 12. All of this here will eventually be our derivative here. And this derivative here is of course very important, because at the end of the day we want this dbe dre. Okay, so this dbe dre will help us to capture our Jacobians, and then we just keep back substituting everything from there. Right, so that's all I wanted to say. It's quite a while, quite long, 50 minutes. Pardon the long video, but hopefully it gives you the background information. Okay, see you next time.